We live in a digital age surrounded by technology that shapes our lives in countless ways. Every click, every swipe, every interaction generates data. This data explosion has revolutionized industries and transformed the way we live, work, and interact with the world. Businesses collect data to understand customer behavior, optimize marketing campaigns, and personalize experiences. Scientists analyze vast data sets to make groundbreaking discoveries in medicine, climate change, and beyond. Governments use data to improve public services, track economic trends, and make informed policy decisions. Databases provide the foundation for organizing, storing, and retrieving data efficiently. Imagine a library with millions of books but no system for organizing them. Databases serve as the organizational framework for the digital world, providing a structured way to store and access data. At their core, databases are organized collections of data. Think of a database as a sophisticated filing cabinet for digital information, where data is organized into tables with rows and columns, much like a spreadsheet. This structured approach allows us to easily search, filter, and analyze data to extract meaningful insights. Whether you're browsing an e-commerce website, booking a flight, or simply checking your bank balance, databases are working behind the scenes to make these experiences seamless and efficient. In today's data-driven world, understanding database fundamentals is no longer just a specialized skill for IT professionals. Whether you're an aspiring data scientist, a budding entrepreneur, or simply someone who wants to navigate the digital landscape with greater confidence, learning about databases can open up a world of possibilities. For those pursuing careers in technology, database skills are in high demand. Software developers, data analysts, and database administrators all rely on their understanding of databases to build and manage applications, analyze data, and ensure data integrity. Business professionals can leverage database skills to make data-informed decisions, track key performance indicators, and gain a competitive edge. Even if you're not pursuing a career that directly involves working with databases, having a basic understanding of how they work can empower you to be a more informed consumer of information. To truly grasp the significance of databases, let's look at some real-world examples of how they are used in various industries. E-commerce. Online retailers use databases to store product information, manage customer accounts, process orders, and track inventory. Social media platforms rely heavily on databases to store user profiles, posts, connections, and interactions. Finance. Banks and financial institutions use databases to manage customer accounts, process transactions, track investments, and detect fraud. Healthcare. Healthcare providers use databases to store patient records, manage appointments, track medications, and facilitate medical research. As you can see, databases are the unsung heroes of the digital age, silently powering the applications and systems we rely on every day. Understanding database fundamentals is no longer a luxury, but a necessity in today's data-driven world. Whether you're taking your first steps into the world of technology or simply looking to expand your knowledge and skills, learning about databases can open up a world of possibilities. In this crash course, we'll demystify the world of databases, breaking down complex concepts into simple, easy-to-understand terms. We'll guide you through the fundamental principles of database management, from understanding different types of databases to designing your own simple database. By the end of this course, you'll have the knowledge and confidence to start working with databases and harnessing the power of data in your personal and professional life. In the vast landscape of databases, data models are like architectural blueprints, defining how information is organized and structured. One of the most common and widely used data models is the relational model, which organizes data into tables with rows and columns, much like a spreadsheet. However, the world of data is constantly evolving, and the rise of big data, cloud computing, and mobile applications has led to the emergence of alternative data models, collectively known as NoSQL databases. NoSQL databases offer greater flexibility and scalability, making them well-suited for handling unstructured and semi-structured data, such as social media posts, sensor data, and log files. These databases come in various flavors, each with its own strengths and weaknesses, including document databases, key-value stores, graph databases, and more. Choosing the right data model depends on factors such as the type and volume of data, the complexity of relationships, performance requirements, and scalability needs. Relational databases have been the cornerstone of data management for decades, providing a robust and reliable way to store and retrieve structured data. Relational databases work in a similar way, using tables to organize data into rows, representing individual records, and columns, representing specific attributes. The power of relational databases lies in their ability to establish relationships between tables, ensuring data integrity and consistency. For instance, in a database for an online store, you might have a customers table and an orders table. The orders table can have a foreign key that references the customers table, creating a link between a customer and their orders. This relationship ensures that every order is associated with a valid customer and allows you to easily retrieve all orders placed by a specific customer. Popular examples of relational database management systems, or RDBMs, include MySQL, PostgreSQL, Oracle Database, and Microsoft SQL Server. As the digital landscape evolves, the limitations of traditional relational databases in handling massive volumes of unstructured and semi-structured data have become increasingly apparent. NoSQL databases emerged as a flexible alternative, offering different ways to organize and manage data beyond the constraints of tables and schemas. Unlike relational databases, NoSQL databases embrace a schema-less approach, allowing you to store data without predefined structures. This flexibility makes them ideal for handling data that doesn't fit neatly into rows and columns, such as social media posts, sensor readings, or log files. NoSQL databases come in various types, each optimized for specific use cases: document databases, key-value stores, and graph databases. NoSQL databases often prioritize scalability and performance over strict consistency, adopting a base model, basically available soft state, eventually consistent. The choice between relational and NoSQL databases isn't a matter of one being superior to the other. It's about selecting the best tool for the job. Each data model has its strengths and weaknesses, and the optimal choice depends on the specific requirements of your application. Consider relational databases if your data is highly structured and relational. Data integrity and consistency are paramount. You need to perform complex queries and joins. Consider NoSQL databases if you're dealing with large volumes of unstructured or semi-structured data. High availability and scalability are crucial. While relational and NoSQL databases cover a wide range of use cases, the world of data models extends beyond these two categories. Graph databases, for instance, offer a unique way to represent and query relationships between entities. Imagine a social network where each user is a node, and connections between users are edges. Graph databases excel at traversing these relationships, making them ideal for social networks, recommendation engines, and fraud detection systems. Other emerging data models include time series databases, optimized for storing and analyzing timestamp data, such as sensor readings, financial data, and server logs. Multi-model databases combine features from multiple data models, offering flexibility and versatility for diverse applications. Imagine trying to read a book written in a language you don't understand. Similarly, to navigate the world of databases effectively, you need to familiarize yourself with its specific language and terminologies. These terms provide the building blocks for understanding how databases are structured, how data is organized, and how to interact with them. Just as a chef needs to know the difference between a whisk and a spatula, a database user needs to grasp the distinctions between tables, records, fields, keys, and indexes. In this section, we'll demystify these key database terminologies, breaking them down into simple, easy-to-understand explanations. By the end of this section, you'll be well equipped to understand the basic structure of a database and the relationships between different data elements. Imagine a spreadsheet with rows and columns, where each row represents a different item, and each column represents a specific attribute of that item. This structured organization is the essence of a table in a database. Tables serve as the foundation for organizing and storing data in a relational database, providing a clear and logical way to group related information. Think of a table as a container for a specific type of entity, such as customers, products, or orders. Each row in a table represents a single instance of the entity, known as a record. Each column in a table represents a specific attribute of the entity, known as a field. In the world of databases, data is organized into meaningful units called records and fields. Think of a record as a complete set of information about a single entity, like a single customer in a customer database. It's like a digital file folder containing all the relevant details about that specific entity. Each record consists of multiple fields, which represent individual attributes or characteristics of the entity. For instance, a customer record might have fields for the customer's name, address, phone number, email address, and purchase history. Each field stores a specific type of data, such as text, numbers, dates, or even images. Fields are like the labels on the file folders within a record, providing context and meaning to the data stored within. They ensure that data is organized consistently and can be easily retrieved and analyzed. For example, having a dedicated email field for each customer ensures that all email addresses are stored in a standardized format, making it easy to search for customers based on their email addresses. The combination of records and fields provides a structured and organized way to store and manage data, allowing you to easily access, update, and analyze information about the entities stored in your database. Imagine trying to find a specific book in a library with millions of books but no cataloging system. It would be a daunting and nearly impossible task. Keys and indexes in a database serve as the cataloging system, providing efficient ways to search, sort, and retrieve data quickly. A primary key uniquely identifies each record in a table, ensuring no duplicates. Like a unique ID for each book in a library, it guarantees data integrity and uniqueness. Foreign keys link related data between tables. Indexes provide quick access to specific information. They speed up data retrieval by sorting fields. Let's consider a simple online bookstore database. Tables, customers, stores customer information. Books, stores book information. Orders, stores customer orders. Order details, stores order details. Relationships, orders linked to customers. Order details linked to orders. Order details linked to books. This example shows how tables and relationships create a structured database. Understanding these concepts helps you build databases and harness data power. Imagine a library where books are added to the collection, borrowed and returned by patrons, updated with new editions, and occasionally removed from circulation. This dynamic flow of information is analogous to how data is managed within a database. CRUD operations, which stand for create, read, update, and delete, form the fundamental actions that drive data manipulation in databases. CRUD operations provide a standardized framework for interacting with data, regardless of the specific database system you're using. Whether you're adding a new customer to a CRM system, updating inventory levels in an e-commerce platform, or retrieving patient records in a healthcare application, CRUD operations are the building blocks of data management. Understanding CRUD operations is crucial for anyone working with databases, as they form the basis for interacting with and manipulating data. These operations allow you to keep your data current, accurate, and relevant to your needs, ensuring that your database remains a valuable asset for your applications and business processes. In this section, we'll delve into each CRUD operation in detail, exploring how they work, their significance in data management, and how to perform these operations using SQL, a standardized language for interacting with relational databases. The create operation in CRUD adds new data to your database. Think of it as adding a new book to the library catalog. In a database, you create new records within tables to store information. Use the SQL insert statement to add data to a table. For example, insert into customers, customer ID, first name, last name, email. Values, 101, John Doe, john.doe at example.com. This keeps your database up to date and accurate. The read operation in CRUD retrieves data from your database, allowing access to stored information. Imagine searching for a book in a library catalog using keywords. Similarly, use queries to retrieve specific data from a database. SQL statements specify columns, tables, and conditions. For example, select first name, last name, email from customers. This retrieves specified columns from the customers table. Reading data is crucial for insights and decisions. In data management, information constantly changes. Customer details update, product prices fluctuate, and inventory levels adjust. The update operation in CRUD modifies existing data, reflecting the latest information. Like updating a book's information in a library catalog, such as correcting a typo. In databases, updates ensure accuracy. Use SQL to update data, specifying the table, columns, and conditions. Just as libraries remove outdated or damaged books from circulation, databases also require the ability to remove data that's no longer relevant or accurate. This is where the delete operation in CRUD comes into play, allowing you to manage your information landscape by removing obsolete or incorrect data. Deleting data might seem like a simple action, but it's crucial to exercise caution. Deleting the wrong data can have unintended consequences, potentially impacting other related data, or even causing application errors. Therefore, it's essential to have a clear understanding of the data you're deleting and its relationships with other data. To delete data from a relational database, you use the SQL statement. This statement specifies the table from which data should be deleted, and any conditions that determine which rows to delete. For example, to delete the customer with customer ID 101 from a customer's table, you would use the following SQL statement. Delete from customers where customer ID =, 101. This statement deletes the row where customer ID is 101 from the customer's table. Similar to the statement, the clause is crucial for specifying the criteria for deleting rows, ensuring that only the intended data is removed. Imagine constructing a house without a well-thought-out blueprint. You might end up with rooms in the wrong places and structural issues. Similarly, poor database design leads to redundancy and inconsistency. A well-designed database ensures data integrity and efficient retrieval. Just as an architect plans a building, a database designer plans for data requirements and growth. This section will guide you through the principles of database design. In the realm of database design, a schema acts as a blueprint, outlining the structure and organization of data within a database. Just as an architect's blueprint defines the rooms, walls, and dimensions of a building, a database schema specifies the tables, columns, data types, and constraints that govern the data stored within. Schema design involves identifying the entities you want to store information about, the attributes of those entities, and the relationships between them. For instance, in an e-commerce database, entities might include customers, products, orders, and payments. Each entity would have attributes such as customer name, product price, order date, and payment method. When designing a schema, it's essential to choose appropriate data types for each column, ensuring data integrity and efficiency. For example, a customer's age should be stored as an integer, while their name should be stored as text. Additionally, constraints such as primary keys and foreign keys enforce data integrity by ensuring uniqueness and referential integrity between tables. A well-designed schema is crucial for data integrity, consistency, and efficient query performance. It provides a clear and logical structure for storing and retrieving data, making your database a reliable and valuable asset for your applications. Imagine trying to describe a complex machine with words alone, without any diagrams or illustrations. It would be challenging to convey the relationships between different parts and how they work together. Similarly, visualizing the relationships between entities in a database can be complex without a visual aid. This is where entity relationship diagrams, or ERDs, come into play. ERDs provide a graphical representation of the entities within a database and the relationships between them. They use a standardized set of symbols to depict entities as boxes, attributes as ovals connected to entities, and relationships as lines connecting entities. ERDs help to clarify the structure of a database, identify potential data redundancy, and ensure that relationships between entities are correctly implemented. They serve as a visual communication tool for database designers, developers, and stakeholders, fostering a shared understanding of the data model. Commonly used notations in ERDs include cardinality, indicates the number of instances of one entity that can be associated with another entity, like one-to-one, one-to-many, or many-to-many. Modality specifies whether a relationship is mandatory or optional. For example, a customer can have many orders, but an order must belong to one customer. Imagine a library where books are shelved haphazardly, with multiple copies of the same book scattered throughout the building. Finding a specific book would be a time-consuming and frustrating task. Similarly, storing data in a database without a structured approach can lead to data redundancy, inconsistency, and difficulty in updating or retrieving information. Normalization is the process of organizing data in a database to reduce data redundancy and improve data integrity. Normalization involves applying a set of rules known as normal forms to the database schema. These normal forms progressively refine the structure of tables, eliminating data duplication and ensuring that data is stored logically and efficiently. The most commonly used normal forms are: first normal form, or 1NF, eliminates repeating groups of data within a table. Second normal form, or 2NF, eliminates redundant data that depends on only part of the primary key. Third normal form, or 3NF, eliminates data that's not dependent on the primary key. Normalization is crucial for maintaining data integrity, reducing storage space, and improving query performance. By adhering to normalization principles, you can ensure that your database is well-structured, efficient, and supports data accuracy and consistency. With a well-defined schema, a clear understanding of entity relationships, and a normalized data model, you're ready to bring your database design to life. Implementing your database involves choosing a database management system, or DBMS, creating the database and its tables, defining data types and constraints, and populating it with data. The choice of DBMS depends on factors such as the type and volume of data, performance requirements, scalability needs, and budget constraints. Popular DBMS options include MySQL, PostgreSQL, Oracle Database, and Microsoft SQL Server. Once you've selected a DBMS, you can use its tools and commands to create the database and its tables, define data types and constraints for each column, and establish relationships between tables using primary and foreign keys. You can populate the database with initial data using SQL statements or import data from external sources. Thorough testing is crucial after implementing your database to ensure that data is stored correctly, relationships are enforced, and queries perform efficiently. Regular maintenance tasks such as backups and performance tuning are essential for keeping your database running smoothly and protecting your valuable data. Imagine a library with no system for organizing books, no checkout process, and no maintenance schedule. It would quickly descend into chaos, with books misplaced, damaged, and inaccessible. Similarly, managing a database without adhering to best practices can lead to data integrity issues, security vulnerabilities, and performance bottlenecks. Just as a well-maintained library ensures the preservation and accessibility of knowledge, following database best practices safeguards your data and keeps your systems running smoothly. Database best practices encompass a wide range of guidelines and recommendations that promote data integrity, security, performance, and maintainability. These practices cover aspects such as data modeling, query optimization, indexing, security, backup and recovery, and performance tuning. While mastering all aspects of database administration takes time and experience, understanding and implementing fundamental best practices from the outset can save you from headaches down the road. By establishing good habits early on, you can create a solid foundation for managing your databases effectively and ensuring the long-term health of your data. This section will guide you through some essential database best practices for beginners, providing practical tips and insights to help you navigate the world of database management with confidence. By incorporating these practices into your workflow, you can create robust, secure, and efficient databases that support your applications and business processes. Imagine losing all your important documents, photos, and files due to a computer crash. Backup and recovery are essential to protect your valuable data from unexpected events. Backups provide redundancy, while recovery restores data to its original state. Establish a robust strategy considering backup frequency, types, and storage locations. Regularly test procedures to ensure data is protected and recoverable. Imagine a library where it takes hours to find a specific book due to inefficient organization and slow search capabilities. Frustrated patrons would quickly abandon their search. Similarly, a slow and unresponsive database can hinder application performance, leading to frustrated users, decreased productivity, and lost revenue. Performance optimization is the process of fine-tuning your database to ensure that it runs smoothly, efficiently, and responsively, providing a seamless experience for users and applications. Database performance optimization is an ongoing process that involves identifying bottlenecks, analyzing query performance, optimizing indexes, tuning database configuration parameters, and potentially upgrading hardware resources. One of the most effective ways to optimize database performance is to write efficient queries that retrieve data quickly. This involves understanding how to use SQL effectively, avoiding unnecessary data retrieval, and leveraging indexes to speed up data access. Monitoring database performance using tools and techniques provided by your DBMS is crucial for identifying potential issues before they escalate into major problems. By proactively monitoring and optimizing your database's performance, you can ensure that it continues to meet the demands of your applications and users, providing a seamless and efficient experience. Section 4. Continuous Learning, Expanding Your Database Horizons. Congratulations on completing this crash course on database fundamentals. You've gained valuable knowledge about the core concepts of databases. The world of databases is vast and constantly evolving. The journey of learning about databases is ongoing. You'll encounter new challenges and discover innovative solutions, explore advanced topics like data warehousing and NoSQL databases. Online resources and certifications can help you delve deeper. Remember, the best way to learn is by doing. Experiment with different database systems and practice writing SQL queries. Explore the vast array of tools and resources available. The more you engage, the more proficient you'll become. Keep learning, keep exploring, and keep pushing the boundaries. Reflect on our journey through the world of databases. Data is the lifeblood of the digital age. Databases bring order to data chaos. We explored data models, schemas, and relationships, mastering SQL for data manipulation, importance of design, normalization, and security, relational versus NoSQL, backup and recovery, performance optimization, and continuous learning. This is just the tip of the iceberg. The world of databases is ever evolving. Use this knowledge as a springboard for further exploration. Navigate the data landscape with confidence. As you embark on your own database adventures, remember that learning is an iterative process. Don't be afraid to experiment, make mistakes, and seek out new knowledge. The more you work with databases, the more comfortable and proficient you'll become. Think of this crash course as a toolbox filled with essential tools for your database journey. You've learned how to use a hammer, a screwdriver, and a wrench, but now it's time to build something amazing. Choose a project that interests you. Whether it's creating a database for your personal music collection, developing a simple web application with a database backend, or exploring advanced concepts like data warehousing or big data analytics, and dive in headfirst. The resources available to aspiring database enthusiasts are abundant. Online tutorials, courses, documentation, and communities offer a wealth of information and support. Don't hesitate to reach out to more experienced database professionals for guidance and mentorship. Embrace the challenges that lie ahead, for they will only serve to deepen your understanding and refine your skills. Remember, the most rewarding journeys are often those that push us beyond our comfort zones and force us to grow. In a world increasingly driven by data, the ability to understand, manage, and leverage data effectively is no longer a luxury, but a necessity. From businesses seeking to gain a competitive edge to scientists making groundbreaking discoveries to individuals navigating the digital landscape, data literacy is becoming as essential as traditional literacy. As you continue your database journey, remember that you're not just learning about a technical subject, but also developing a valuable skill set that will serve you well throughout your personal and professional life. The ability to think critically about data, identify patterns, draw insights, and communicate effectively using data is in high demand across various fields and industries. Embrace the power of data. Use it to make informed decisions, solve complex problems, and create innovative solutions that benefit yourself and others. Remember, data is not just a collection of facts and figures. It's a story waiting to be told, a puzzle waiting to be solved, a potential waiting to be unlocked. As you venture forth into the exciting world of databases, carry with you the knowledge, curiosity, and determination to make a difference. The future of data is in your hands. Go forth and create something amazing.